Welcome back. I'm going to now look at a couple of examples on conditional probability and independent events. Um, let's say that we have internet site. We're looking at internet sites. The internet sites often vanish or move, so that references to them can't be followed. In fact, 13% of internet sites referenced in papers in major scientific journals are lost within the 2 years after publication. If a paper contains 7 internet references, what's the probability that all 7 are still good 2 years later? Uh, and what specific assumptions do you make in order to calculate this probability? So again, what we are saying is that 13% of internet sites referenced in papers are lost within 2 years after publication. So the probability that um, a internet site referenced in papers will be lost in 2 years is 0.13. And the probability that a internet site referenced in papers will not be lost in 2 years would be 87% or 0.87. Um, so we want to know what's the probability that 7 internet references will be good after 2 years. And so here I'm gonna have to make the assumption that the so the probable so we are going through the 7 references. So the probability that the first reference will not be lost is 0.87. The probability that the second reference is not going to be lost is 0.87, and so on. So if I assume independence, then the probability that all 7 are still good after 2 years would be that we multiply 0.87 7 times. So if we multiply 0.87 7 times, um, so we multiply 0.87 times 0.87 times 0.87 times 0.87 times 0.87. So if I multiply 0.87 with itself 5 times, then I get about 0.5, 0.498. So that's about 0.5. So so the probability that probability that 7 references um, uh, are good after 2 years is going to be about 0.5. So again, the assumption that I made here is that um, the references the references are independent of each other. So that knowing whether one of them is lost or not lost doesn't have any effect on another reference being lost or not lost. Here's another example. The random walk theory of securities prices holds that price movements in disjoint time periods are independent of each other. Suppose that we record only whether the price is up or down each year, and that the probability that our portfolio rises in price in any one year is 0.65. So the probability that the portfolio rises in a year, in any one year, is 65%. And so the probability that the portfolio goes down in price would be 35% or 0.35. Um, so this probability, it turns out that approximately is correct for a portfolio containing equal dollar amounts of all common stocks listed on the in the NYSE, listed on the NYSE. So what we want to know is what's the probability that the portfolio goes up for 3 consecutive years. Well, again, so we're going to use the statement here that says that the price movements in disjoint time periods are independent of each other. So we have 3 periods here. Period 1 would be the first year. There are 3 consecutive years, so first year, second year, and third year, and they are disjoint time periods. So the price movement in the first year um, um, is independent. The price movement in the second year is independent from the first. The price movement in the third year is independent from the price movements in the first 2 years. So assuming this independence, then what's the probability that the portfolio goes up for the next 3 consecutive years? Well, the probability that the portfolio rises up, goes up in any one year is 65%. So basically, we multiply 0.65 with itself 3 times, and so what we do then is we basically have 0.65 times 0.65 times 0.65, and if we do the calculation, we're going to get about 0.274 or about 0.27, let's say. So the answer would be about 0.27 here. Okay, here's another question. If we know that the portfolio has risen in price 2 years in a row, what's the probability? What probability do you assign to the event that it will go down next year? So again, because we are saying that the price movements in disjoint years are independent of each other, as a result, we're going to say that in this case, the probability that the portfolio will go down next year will be 0.35. That is, it doesn't change just because we know what happened in the previous 2 years. So the answer in this case would be 0.35. The next question is, what's the probability that the portfolio's value moves in the same direction in both of the next 2 years? Well, in the next 2 years, then, okay, so then what we can say is that either it goes up. So basically we're saying what's the probability that in the next 2 years, the portfolio's value will go up in both years, or it's going to go down both years, right? So down on both years, or up on both years. And so this would be the probability that the value goes up in both years plus the probability that the value goes down both years. And the probability that the value goes up both years would be 0.65 times 0.65, and the other one would be 0.35 times 0.35. And again, that's because we are assuming independence, so the probability that the value goes up both years would be the same as the probability that the value goes up first year and the value goes up second year, which are both 0.65, again because of independence. So now we just calculate what that is. So 0.65 times 0.65 plus 0.35 times 0.35, and that's 0.545, or you can say about 0.55. Okay, so the answer would be about 0.55. Okay, so let's go to the next question. So let's say that Slim is still at the poker table, and at the moment he wants very much to draw two diamonds in a row. As he sits at the table, looking at his hand and at the upturned cards on the table, Slim sees 25 cards, and the only diamonds are the three in his hand. What's the probability that the next two cards dealt to Slim will be diamonds? This outcome would give him five cards with the same suit, a hand that is called a flush. Okay, so Slim is still at the poker table. At the moment, he wants very much to draw two diamonds in a row. Again, as he sits at the table looking at his hand and at the upturned cards on the table, Slim says 25 cards, and the only diamonds are the three in his hand. So, um, so notice that how many cards are left then. Uh, we have well, so there are 13 there are 13 cards of diamond, right? So the 10 of them are still not upturned, and there is a total of 27 cards that are still on the table but not upturned. So the probability that the first card is diamond and the second card dealt to Slim is also diamond is equal to the probability that the first card is a diamond and times the probability that the second card is a diamond, given that the first card is a diamond. And so the probability that both cards are diamond is going to be, well, what's the probability that the first card is a diamond? Well, that's 10 out of 27. Because again, 27 cards are still on the table that will be from which cards will be dealt to Slim, and 10 of them are diamond. And then once one card is once he gets a diamond, then the probability that the second card dealt is a diamond would be 9 out of 26, because 26 cards are left now and only 9 of them are diamond. So at the end we get this 5 over 39, which is 0.182, or approximately 0.13. So here we are using the conditional probability. So again, the probability that both cards dealt to Slim are diamond is equal to the probability that the first is a diamond and multiplied by the probability that the second is a diamond, given that the first is a diamond. So the second one here is the conditional probability. Okay, one last example. So let's say that so we're looking at breast cancer screening. If a woman in her 20s gets screened for breast cancer and receives a positive test result, what's the probability that she does have breast cancer? So it turns out, so we have this figure where it tells us basically that the probability that a woman has cancer is 0.0004. The probability that a woman doesn't have cancer is 0.9996. And the probability that someone who has cancer will test positive is 0.8. Probability that someone who has cancer will test negative is 0.2. Probability that someone who doesn't have cancer will test positive is 0.1. And the probability that someone who doesn't have cancer but will test negative is 0.9. So if someone has cancer but tests negative, that's called a false negative. And someone who doesn't have cancer but tests positive, that's the case we call false positive. A person could either have a positive test and have breast cancer, or have a positive test but not have cancer. Okay, so the probability that of cancer, like I said, is 0.0004 here. The probability that a woman doesn't have cancer is 0.9996. Probability that someone who so this is the conditional probability of a positive test given that the person has cancer is zero point 0.8, and the conditional probability that someone tests positive given that she doesn't have cancer is 0.1. So this is the probability of a false. So this one right here, that's the probability of a false positive, right? So this is the probability of a false positive here, 1%. 10%. The So the probability that a woman has cancer and tests positive, uh, we can find that by using the multiplication formula, which says this would be equal to the probability that a woman has cancer times the conditional probability that a woman has cancer. The conditional probability that a woman tests positive given that she has cancer. So so we get that this is 0.0004, and then the probability that a woman tests positive given that she has cancer, that's 0.8. And so we can find that easily. And what's the probability that a woman has no cancer and tests positive? Well, again, by using a multiplication formula that we saw before, so this is given by the probability that a woman has no cancer times the probability that a woman tests positive given that she doesn't have cancer. And so when we multiply them, we get 0.9996 times 0.1. And we can, one can easily simplify that. Okay, so this is where we are right now. The So now what I want to find is the probability that a woman has cancer given that she tests positive. So given that a woman tests positive, what's the probability that she has cancer? Well, by using the formula for the conditional probability, this would be the probability that a woman has cancer and tests positive divided by the probability that a woman tests positive. Now, the probability that a woman tests positive can be written as the probability that a woman has cancer and tests positive plus the probability that a woman has no cancer and tests positive. So the denominator here is the probability that a woman tests positive, which can be broken up into two terms like this. So then we already know the numerator is 0.0004 times 0.8 from the previous slide. And in the denominator, we know each of the terms from the previous slide. So 0.0004 times 0.8 plus 0.9996 times 0.1, and that's 0.3%. So given a so here again, given a positive diagnosis, there are two possible outcomes. So positive test and the breast cancer, or positive test and no cancer, which is what we applied in the denominator here. Okay, so this is it. That's all the examples that I would like to do. And again, the references here, we are following the text by the Moore, McCabe, and Craig. Okay, so that's the end of my discussion here. So I'll see you in the next video.